1.4, increasing and decreasing max-mins in behavior. So most of this lesson is a review from Algebra 2, but we've talked about increasing and decreasing intervals before. And when you talk about increasing intervals, we are talking about when the graph appears to have a positive slope, when it's moving upward from left to right. Positive slope. Or upward from left to right, or downward from when you're looking backwards. So the positive slope direction. A graph is decreasing when you see a negative slope direction. Negative slope, which means decreasing from left to right or up if you're going left. And a constant graph is when it's horizontal from left to right and there's no increase or decrease. Now when we're labeling intervals for increasing and decreasing, we look at the x values. We look at the domain, and we talk about it just in terms of the domain. And like on this first one, for this next one here, we have increasing. This graph is increasing here and here. That's when I see positive direction slope values. So this was looking at this x intervals, -1, -2, everything before -3. So it's from negative infinity until -3. And you can never reach an infinity or negative infinity. And the -3, it all depends. Some textbook and authors say, yes, you put in a bracket. Some say a parentheses that you say you don't worry about the endpoint. I'm under the opinion where let's not worry about the endpoint. It won't be a mistake if you put it. The only thing that's bad is if you ever include an endpoint when it's an undefined value, then it couldn't be. But on a solid point like this right here, it could be a bracket or a parentheses. And I'd say let's just use a parentheses. And I wouldn't count off for that if you put a bracket. Also, from 1 to 1, 2, 3, 4. From 1 to 4, this function was also increasing. And so 1 to 4, and that's why I would use parentheses, not worry about the endpoints. Like I said, it depends on the author. Some textbooks and authors say, yes, count the endpoints. Some say, don't worry about the endpoints. So if this function is decreasing, when you see a negative slope, which is from there to there, which is from -3 until 1. And a constant looks like from 4 to infinity. 4 to the right, this graph is leveling off. On the next one, I see increase here, which is from -4 until -2. And I also see an increase from here to here, which is from 1 to 3. And I see a decrease in between there, which is from -2 until 1. And there's never a spot where this graph levels off. So this is none or NA, whichever way you want to write it, does not matter. And on the last one in this section, this graph is a rational function. Rational functions, if you remember, have a horizontal asymptote that they never touch. They also have a vertical asymptote that they never touch. And so this graph is getting closer and closer and closer to that horizontal asymptote, which it never gets there. So this, from negative infinity until 0, which it doesn't exist at 0, so negative infinity to 0, we are increasing because we're going upward with a positive slope. And this is one of the times you could never have a bracket because we can't equal 0. But then also, after 0, this graph still just keeps increasing. So 0 to infinity is also an increasing function. And since that's the entire domain of this function, that it was increasing, it's never decreasing and it's never constant. And let's move on to Extrema next. So for the next section, let's talk about Extrema, which are called max and mins. The relative max and relative min, or absolute max and absolute min. Extrema is plural. Extremum is the singular version of that. For absolute, it can be a synonym with global. Absolute or global maximum means the highest point on the entire graph. So you look for where is the highest point the graph ever goes. That's an absolute maximum or global maximum. And infinity, you can't actually get to infinity. So if a graph goes up forever, it has no absolute maximum because infinity is not an actual value. And same thing for global minimum. The absolute or global minimum is just the lowest point on the entire graph. Well, the term relative maximum is also a nickname for local maximum. A relative or local minimum, this one's maximum, is the top of any little hump there, any time that it switches from increasing to decreasing. So if the relative and absolute could be the same point, like this one's a relative maximum and an absolute maximum. this one is only a relative or local maximum. It has the top of a hump. Now, for this is neither, because it's increasing and then increasing again. It has to switch from increasing to decreasing to be a maximum. So the top of the hump, the top of a curve. A relative minimum has to be the bottom of any hump. So here's a relative minimum. This is not a relative minimum because it doesn't switch from going down to going up. It's just at the edge. And same thing here. This is never switches from decreasing to increasing. So the only relative minimum is that one right there on this graph. Now, many times we're going to use the calculator for this. Sometimes we'll make the graphs easy enough to see where you can look at it and tell what the answers are. But for this test, or this assignment, we do need to know how to find these on a calculator. So, looking at this graph right here on the left, I see that it has arrows going down forever. That means there is never an absolute minimum. There's none or not applicable, because you can't get to the bottom. You can't get to negative infinity, so that's not an actual value. And there is an absolute maximum. It's right in here, and we'll have to calculate that in a second. And a relative maximum is the same thing. These are the same ordered pair, because the same point, because that's the top of a hump and it's the highest graph point on the entire graph. The relative minimum is the bottom of any hump, and this graph never switches from decreasing to increasing, so there's not a relative minimum. So to calculate that value, we're going to go to use a calculator, and that is negative x to the fourth minus 2x. I need that. So I'm going to go to a blank graph and go negative. Oh, you can't see all my calculators. So let's make this, try to make it where you can see this at least. Oops. If I can get this large enough for you. There we go. Negative x raised to the fourth minus 2x, I believe. Let me double check my math. Negative x to the fourth minus 2x. And then, oh, I wasn't paying attention. Negative x to the fourth minus 2x. Not all up in the power. I had to make sure. Well, there's that same graph. To find a maximum or minimum on these calculators, we go to Menu, analyze the graph, and we have to know whether we're looking for a maximum or minimum. We said we're looking for a maximum because this graph had no minimum. So then when it says lower bound, you click somewhere before the maximum, and then upper bound, click somewhere after the maximum, and then it tells you the value. Mine is set to show several decimal places. If yours doesn't show enough decimal places, you can always go Document and go to, Settings. Let me hold on, escape and get math. Document, Settings, Document Settings, and make this go to float at least 6. And then you can see more decimal places. So if you ever need at least 3 decimal places, I always float to 6 or 7 at least, which mine's already there. Come on. And so the maximum value is the y value, which is 1.191. And that occurs at 0.794, negative 0.794. So the maximum value is the y value of 1.191. Maximum 1.191, and we say at x equals, the x value was negative 0.794. Whoa, wrong way. Negative 0.794. Now for calculus, or for pre-calculus, honors pre-cal, we want to go to at least 3 decimal places usually, unless, like the assignment, sometimes we'll make you do less. But in AP calculus, everything is always correct at 3 decimal places. Well, the relative maximum is the only maximum here, so it's the same as the absolute maximum in this case, which is 1.191 at x equals negative 0.794. Now let's look at this next one. I look at the graph first and say, do we see a highest or lowest point on the entire graph? And I see this has arrows at both ends. It goes up forever and down forever, so there is no absolute max or min, because it's going towards infinity and negative infinity, which is not an actual value. But it does have a relative minimum and a relative maximum. So let's graph this one. So that is x to the 5th. I'm going to come back and forth on this. So I'm going to go home and get a new graph. So new graph, x raised to the 5th power, get out of the power, and then it said minus 2x cubed minus 2x raised to the 3rd power, get out of the power, and minus 2x squared. Minus 2x, whoops. Whoa. Come on. Sorry about that. Minus 2 x squared. And that graph looks very similar. So let's find the maximum first. To find this maximum, we go Menu, Analyze, Maximum, get somewhere before it, click, get somewhere after it, click. That maximum is a maximum value of 0 at x equals 0. Relative max is 0 at x equals 0. To find the relative minimum, I'm going to look for this point over here, and we go Menu, Analyze, Minimum, and get somewhere before it, get somewhere after it. And most of your calculators at home, or Desmos should give you at least 3 decimal places, but this, and Desmos, you would just click on those points and they tell you the values. We want negative 0.4083, negative 0.4083, or 408 is 3 decimal places. I think, was it? Let me double check. 4.083. I wrote it right and said it wrong. If I can undo. Negative 4.083 at, that's my at sign, at x equals, and that x value was at 1.34, and you don't have to, if the third digit's a 0, you don't have to put it. So 1.34. 1.34. Now, if you ever need on a graphing calculator and it's not showing you 3 decimals, because many of your calculators, I noticed when I did this lesson, or this question, it didn't show 3 like mine shows. So one option you can do is you can click on that and hit Control var and then say store that as like any letter you want. I picked A. And then click on that one, Control var to store, and store that one as B. And when they're bolded, it shows you they've stored them in memory. And then, as long as I don't go to Scratchpad and I go to like a blank calculator page, I can say A and B, and it'll tell you at least 3 decimal places. So if you ever need more decimal places, you can store it in the calculator's memory. And those stay in the memory until you start a new document. Okay, well, let's move on to the back side. End behavior is the new concept for pre-cal compared to the rest of this was a lot of Algebra 2 review. And what this is saying, end behavior is saying that we want to look as we go to the right of a graph forever and to the left of a graph forever. Not worried about what's going on in the middle, just as we go, as x goes to negative infinity. Well, negative infinity on the x means going left. So this is saying just look to the left. And as x goes to infinity means look to the right. As we go out to the right and to the left, what are the y values doing? F of x is the y's. Are they going up? Are they going down? Or do they level off at a number? So, reading this first example here, as x goes to negative infinity, as x goes left, where's the y value going? And we look at this graph, as we trace it back, that y value is going upwards, so we say infinity. And then the second line says, as x goes to positive infinity, as x goes out to the right forever, where's the y value going? Well, it's still going up, so this is infinity both directions. On the next one, as x goes towards negative infinity, as we go this way, trace that graph, where are you going? Well, you're going up forever, so that's positive infinity as we go left. But as we go right, as this graph goes to the right, the y value is going down to negative infinity. And on this third one, I see a rational function. Hopefully you remember a rational function has a horizontal asymptote and a vertical asymptote. So this graph gets closer and closer and closer to this asymptote, but it never touches it. And that asymptote, in this case, levels off at -2 both directions. So that is our horizontal asymptote. This function leveled off at a solid number, and it's at the horizontal asymptote. Now, without a graph, we have to use what we learned. We did learn the end behavior, kind of. We learned how to find horizontal asymptotes back in Algebra 2 with. We use the acronym Bobo, Bachu, and Betsy for bigger on top means the graph bigger on bottom, levels off at 0. Bigger on top means there's not a horizontal asymptote. And if the bottom equals the top, we look at the leading coefficients. So, looking at this first one right here, when we're looking for, as x goes to negative infinity, x goes to positive infinity, we're looking for what happens to the left and to the right. And this, the degree is 1, and this, the degree is 1. So, it's infinitely bigger. That's just going to a huge number, and that's going to pretty much the same huge number. Think of $1 billion plus 1 or $1 billion minus 2. You still have basically $1 billion in the numerator and the denominator. So those, you don't worry about the plus or minus number. You look at this divided by this coefficient divided by this coefficient, which is 1, and that's where that graph levels off. It's a bottom equals top. It's a Betsy. Bottom equals top. So we look at the coefficients. I'm going to go down. So this one, the degree on top, that's x to the 0 because there's not one over x squared. So that's bigger on bottom. Bigger on bottom levels off at 0. And if you kind of think about what's going on mathematically on this one, let me give you an example. If I just move that to 1 instead of 0.8, round it up to 1. 1 divided by 10, 1 divided by 100, 1 divided by 1,000, 1 divided by, let's get even bigger, 10,000, and we could keep going. Well, this is 0.1, this is 0.01, this is 0.001, this is 0.0001. Oops, I dropped my pen. As that denominator keeps getting bigger and bigger and bigger, the decimal number keeps getting smaller and smaller and smaller, and that's why when it's bigger on bottom, the graph levels off at 0. The horizontal asymptote will level off at the x-axis. Now, I missed a perfect opportunity on these notes. I should have, so that answer was 0 for both of these. But I should have made an example problem instead of saying 0.8 over x squared. I should have said 0.8 over x squared plus 3. Well, this still goes to 0, but now it's shifted up 3. So it would level off at 3, going both directions. Or if I had said minus 31, then that graph would shift down 31, so the horizontal asymptote would be negative 31. So just to refresh your memory on those, I wanted to kind of talk about that. Well, let's work our way around. We're going to do this one next. So this is a degree of 2. This is a degree of 2. It means we don't have to worry about any of those extra stuff. We look at the leading coefficients. So 4 over 1. So this graph has a horizontal asymptote at 4. So both directions it levels off at 4. And now finally, this one has a degree of 2 and a degree of 1. So it's bigger on top. Bigger on top means there's not a horizontal asymptote. So what that means is the graph is either going to go up to the right or down to the right. And same thing on the left. It's either going to go up or down. It's going some direction. I just don't know which. So we could graph it on a calculator, which would be the quickest and easiest way. And since we did most of the relative max and mins with the calculator, the chance of being able to use the calculator would be good. Graph it and see if you see the graphs going like this, or if it's even doing this kind of like as long as the left end and right end, we can decide. Or is it doing this, up on the right and down on the left? So one way would be graph it. But I'm going to show you how to do it without a calculator. And that's the last one. So without a calculator, I know that dividing by 0, we have a vertical asymptote at 0. So I'm going to pick some 1 and 2 to go to the right to see, is this going up or down? So if I make numbers like 1 and 2, let's plug in 1, then we'll plug in 2. If I plug in 1, you get 4 times 1 is 4 minus 3 times 1. So 4 minus 3 is 1 minus 1. You get 0. 0 divided by 11, which is 0. If I plug in 2, that's 4 times 4 is 16. 3 times 2 is 6. 16 minus 6 is 10 minus 1 is 9. You get 9 over 22. Well, is that bigger or smaller than 0? That's bigger, so this graph's going up to the right. So as x goes to the right, we're going upward to infinity. Well, now I need to know what's happening as the graph goes left. So I'm going to plug in negative 1, then plug in negative 2. So let's make another little table here. If I plug in negative 1, that's going to be positive 1 times 4 is 4. That's going to be negative 3 times negative 1 is positive 3. So 7 minus 1 is 6 for the numerator, and negative 11 on the bottom. If I plug in negative 2, well, that's going to be 4 times 4 is 16, plus 6 minus 1. So it's 22 minus 1 is 21 over negative 22. Well, this is just under a half. This is really just almost negative 1. So if we're at close to negative 1/2, then we're close at negative 1. Negative 1/2, negative 1, this graph is going down. So this would be negative infinity as we go left. And that's how you do it without a calculator. Easier, like I said, it's easier way, plug it in and graph it and see what it looks like, and you can get the answers. But that is everything you need to be able to do this assignment. Good luck to you.